Last time we were together, we discovered that if you take an area that's under a curve and you divide that area up into trapezoids, and then of course find the... Last time we were together, we discovered that if you take an area that's under a curve and you divide that area up into trapezoids, and then of course find the area of each of those trapezoids and add all of those areas of those trapezoids, you end up with a pretty interesting yet simple formula that says basically that you're just going to add the y values, which represent the bases of each of those trapezoids. And of course the y values in the middle, they get shared. And that's why we find ourselves doubling those y values. But the y values at the beginning and end, well, they only get used once in each trapezoid. And then we get h, which turns out to be the thing that is the most nemesis for kids. But let's just understand that h is the length of the subinterval, which comes from taking the whole interval, b minus a, and dividing it by n, dividing it by the number of subintervals so that we can get this equal length of each subinterval. We'll call it h, which of course is the height of the trapezoid. So how do you use the trapezoid rule? How do you use it to actually approximate an area? Well, I think you'll find that it's pretty simple because we only need y values and h. Now, if you see a problem that says to use the trapezoid rule to estimate an integral, well, then we don't want to do an antiderivative. We want to be thinking about, obviously, the trapezoid rule. Now, I hope you realize that I've been big on sketches in this chapter. It turns out that if we think about a sketch of this problem, if we think about a parabola from 2 to 3, there wouldn't be anything wrong with that. But the thing is that we don't actually need to divide this thing up into 4 trapezoids and kind of reinvent the wheel. All we really need to do is realize that there's an h and there's y values. So let's get rid of the sketch and let's find h. I want to make this as simple as possible. H is going to be the length of the subinterval, which is going to be just, in this case, 3 minus 2, divided by the total number of subintervals. In this case, we're going to use 4. Now remember, that really means that we're using 4 trapezoids, but now we know that each trapezoid has a height, or each subinterval has a length of 1/4. Next, we need some y values. Now I stole this from a student, but they don't care because we're all here to help each other. But basically, to find y values, we could go back to a good old table of values. It's such a simple concept, but so helpful in this problem. It helps us to organize our y values. Now, of course, the y values come from x, and x starts at 2. That's, of course, our first, the beginning of our interval. And then, do you realize how the quarter is going to help us to get the next x value and the next after that? Well, certainly, we're just going to know that the next x value is at 2 1/4. The next one's at 2 1/2, 2 3/4, and then to 3. Well, it's time to find y values. And how do you find y values? That's right, by plugging into the function. So we're going to plug in 2, and of course that gives us 4. We're going to plug in 3. Of course that gives us 9. And the rest of them we could use a calculator for. And make sure that you understand, for example, if I plug in 2 1/2, 2 1/2 squared is just going to be 6 1/4. And if I square some of these other values, it gets a little messy. I'm choosing to write them as decimals this time. Certainly you could work with the fractions if you wanted to. Well, we have ourselves an h, and we have ourselves some y values, so it's time to plug into the trapezoid rule. Now the trapezoid rule says that the area, sometimes we'll call it the trapezoidal area, just to make it a little more descriptive, is always going to be h over 2. Now, I'm telling you, this is like the main thing that kids have trouble with. There's always a divided by 2. and there's always an h. And, well, we found our h to be 1/4. So in a problem like this, what we got to be careful about is that we are putting in both the 1/4 and the divided by 2. If you want to know the mistake that people make, they forget to divide by 2 because they kind of already see a division sign. They already see the 1/4. Oops, I don't want an equal sign there. Now it's time to start adding up some y values. Of course, I'm only going to use the first y value once, but I'm going to use each of these next y values twice. If I can kind of squeeze this in here, we're going to use 2 of those 50625s. We're going to use 2 of these 625s. Now, sometimes people say, could I just pop this in a calculator? My answer to that is yes, but you're going to need to show at least one step. You can either show the step that I'm showing here, or you can show the result that you get from adding these on your calculator. Okay, so again, if I'm going to show a step, I need to either show what I just set up or the line that I'm putting here right now, which would be 1/8 times 50.75. Now be careful. Make sure you're playing along. You might just want to practice and put those in your calculator, but pretty much just some adding and multiplying. And if you take 1/8 of 50/75, you end up with 6.34. It comes out as a terminating decimal, just 6.34, and that's the estimated area of that space that we erased under the parabola. I wonder how close it is to the actual area. Well, we're going to find out. And of course, the actual area comes from the actual antiderivative. And if we find the actual antiderivative of x squared, well, it's one of the first ones we've ever done. Just add to the exponent and divide. And I can plug in f of b and f of a. Of course, that's going to be f of 3 and f of 2. 3 cubed is 27 thirds. Yes, I know that's equal to 9, but we're going to leave it because 2 cubed is 8 thirds. And if you subtract these two numbers up here, we're going to end up with, I'm kind of using my equal sign loosely here. I should have put an integral sign. Let me do this the right way. So the integral of our function is going to be 27 thirds minus 8 thirds. Since I already have a common denominator, I can get 19 thirds. And if you're good with your decimals of thirds, you know that that's 6.33 repeating. Pretty close. That is 634 was pretty close to my actual answer. It was just a little bit of an overestimation. Now, it's an overestimation for obvious reasons, but it's also an overestimation because of concavity. Let's think about this a little bit with concavity, if you will. You see, if I have a graph that is concave up, like a happy little parabola, well, anytime I draw trapezoids in a graph that's concave up, my trapezoids are going to be a little bit too big. So we always end up with an overestimation for concave up. Now I know you already can see the answer here, but if you think about concave down is a graph that opens in this manner. And if you think about drawing trapezoids under there, well, any trapezoid that you draw under a concave down graph is always going to be a little bit too small. And so we'll end up with an underestimation if it's concave down. What about if it's exact? What about if it has a no concavity? What about if it's a straight line? Well, of course, if it's a straight line, we know that we're going to end up with a perfect trapezoid that fits perfectly under that graph. And that's why if there's no concavity, then we have an exact estimation. Now, the trapezoid rule. It's a great way to estimate. And obviously, we can do that for an equation. But we already know that we can find the actual answer for an equation. That's what we spend a lot of this chapter doing. So why do I really need to estimate? Well, it's more than just because the teacher says so. Honestly, the reason we estimate is if we don't have an equation, That is, if we just have data or maybe some type of shape that can't be turned into a quick equation, like Lake Pi. Have you ever been to Lake Pi? Oh, it's a great place to go. It's the temperature of the water is always 3.14 degrees, or 3.14 degrees. I was going to say Celsius, but that's pretty cold. How about the depth of Lake Pi? Yeah, the depth of Lake Pi is always 3.14 feet. And the shape of Lake Pi, well, it's in the shape of pi. What if I wanted to find the area of Lake Pi? And what if all I knew about Lake Pi were some measurements? Maybe like measurements that were taken every 50 feet. And every 50 feet, starting at 0, I took a measurement. And maybe I discovered that at this spot, it was 85 feet across Lake Pi. And then 50 more feet down the lake, I measured and found that it was 90 feet across. And then 50 feet down the road, I measured, and of course here it's going to be really long, so we have 200 feet. Now, every 50 feet, I measure the width of the lake. Obviously, I'm just kind of making this up, but do you realize what these numbers represent? That's right, each one of these measurements is like a y value. I should have shown the first y value to also be 0. And that's all you need. That's all you need to find the area. It's actually really amazing. All I need is, well, the length of the subinterval, which is going to be 50, and then each of these y values. And if I have those two numbers, I can plug them into the trapezoid rule, and I can find a really good estimation of the area. We just did it for a parabola. It was almost perfect, so there's no reason I can't do it for any list of data points. So what do you think? H divided by 2? You weren't going to forget to divide it by 2, were you? And then you take each of the y values. Of course, you take twice the y values in the middle. Did you notice that I still use 0 as my first y value, since that's where my first measurement was taken? But I'm just going to double all these y values. Double 200, double 80, double 170. Don't forget to double regular 70, and then 0 is my last y value. It's almost too easy. You just got to trust it. So we end up with 25 times 1390. By the way, 1390 is like the sum of all those y values of all those trapezoids that we sketched in the first lesson. And 25 times 1390 is 34,750 feet squared. That would have been cool if that answer came out to be like somehow 3.14, but it didn't. But it's still a good estimation. Now, with the trapezoid rule, it opens up the possibility for us to find the area, if you will, of any shape that we can measure its y values. And as a small project in this last section, I'm going to have you guys use the trapezoid rule to find the area of a pretty popular shape, a window that's on your favorite car. And I'm going to describe that briefly in the next video.